Hey, this is Brock Lemire's, and we're continuing our study of embedded systems design. In this video, we are going to look at the next class of instructions, which is called the data manipulation class. And these are going to be instructions that alter information using the ALU. And we'll specifically look at the add instruction in this video. Okay, so, arithmetic instructions will be the first class that we look at, but more importantly, just think about the ALU. So, up until now, we haven't looked at anything that's used the ALU really. And the ALU can be thought of as a collection of combinational logic circuitry that performs anything that you want it to do when you're designing the processor. So the makers of the MSP430 said, well, we probably should have some circuitry to do an add. And so they build an addition circuitry into the ALU. And then they said we probably need one that should perform a logical and that is circuitry in the ALU. And so it sits down here and it can operate on information coming from CPU registers, and it can also operate on, well, it operates on CPU register information, and the output can either be fed back into a CPU register or it can actually be put out on the memory data bus so that the result can go as a destination somewhere else. And then using some bus manipulations, you can also do operations on information directly in memory. Every instruction, so the way I think about it is every operation that is supported within the instruction set is implemented within the ALU. And so I just think of the ALU as a big combinational logic circuit. There are registers in there to register the data, but that's the way you can conceptualize it. Of major importance, though, is that the ALU contains status flags, or it generates status flags to give you more information about the current operation. And the status flags that are implemented on almost every computer, but we'll look specifically at the MSP430, are the four flags called the carry flag, the zero flag, the negative flag, and 2's complement overflow flag. 2's complement overflow is given the letter V. I don't know why, honestly. 2's complement overflow, maybe? I don't know why, but it's V everywhere. And what these do is every operation in the ALU might set these, okay? And so when you look at an instruction, you want to look at the data sheet and see, does this actually alter any of these flags? And if so, how? But when we look at an add instruction, for example, it's important that the result, if it generates a carry, we need to know that it did that. And so it uses this C flag to indicate that the result generated a carry. We also can look at whether the result was a 0, whether the result was negative, and negative means for the width of the operation that you are conducting, whether it's a 16-bit operation or an 8-bit operation, is the most significant bit of the result a 1. Now, that's all it does. Whether or not you are using 2's complement numbers for signed numbers or unsigned numbers, that's up to you to keep track of. The end flag is going to just assume that you are using 2's complement numbers, and it's going to set or not set based upon the most significant bit of the result, which is always a signed bit if you are using signed numbers. Same thing with 2's complement overflow. It doesn't care if you're using 2's complement numbers or not. It's going to assume you are and generate that bit based upon that. Okay, the carry flag can also be used as a borrow when doing subtraction, and we'll look at that in a later video. But these flags that exist are in the status register in the CPU. So the ALU generates them, and then they are latched into the status register, and they remain there until the next instruction, which alters them, updates them. Okay, so you can have an instruction that sets these up accordingly, and then you can have a bunch of instructions, for example, move instructions that don't alter these status flags, and you can then go back and look at them later and make decisions. We are going to use these a lot when it comes time to look at conditional jumps, because we can look at these and decide whether to jump over certain sections of code depending on what happened here, or execute certain sections of code. Okay, so keep that in mind. Let's look at our first instruction. Let's look at the add instruction. The mnemonic is ADD, and it is going to do exactly what you think. It is going to add two numbers together and produce a sum. This works on signed and unsigned numbers because if you remember, the addition logic is identical regardless of whether it's signed or unsigned numbers. You can do a 16-bit add or an 8-bit add by appending .w or .b to the end, and it's pretty simple. It's a nice instruction to start with. When I look at an instruction for the first time, I always want to come in here and think about, I look up at this table that I generated from the data sheet. This is basically, I just retyped in a table from some of the documentation provided by TI. And if I look at add, I first look at how it works. So the behavior. It's going to add the source operand to the destination operand, and it will put the sum back in the destination operand. That's very important because whatever you use for the destination, it's going to be overwritten by this instruction. The source will not, but the destination input is going to be gone. And it sets all 4 of the status flags. So that is the important part. This is really key. When you look at each instruction, you got to know what's it doing with those status registers. Okay, so let's do an example. Okay, so let's just do some simple additions and we'll watch the sum be generated. We'll go ahead and watch the status flags in the debugger, and we'll do some additions on various number formats. So we'll start with like some decimal additions, some hex additions, and we'll look at some that generate the carry flag, some that set different flags, etc., etc. So let's do it. Let's fire up CCS. So bring up CCS, and here we are. And let's see. So what we're going to do is let's fire up. Go ahead and make sure your MSP430 is plugged in. Make sure the launch pad's plugged in. And let's start a new project. So I'm going to come up here. I got the right MCU setting. And let's go ahead and call this ASM. And I'm going to put ALU. Okay. And that's just going to represent that this is data manipulation instructions. And it'll kind of keep all these projects lumped together. And then I'll put ADD, that indicating that this is going to do an add instruction. Empty assembly only project, and go ahead and finish. And it will go ahead and create our new project, and it will create our blank template for us. Let's scroll down to the main loop area and go ahead and put main and then jump main, and that forms our infinite loop. And now we can put some instructions in here. And let's do the example. Let's do this example right here. Let me get this over here. Let's see. So we're going to do these adds. And the first thing, let's do three, we'll do 3 16-bit adds first, so I'll keep these kind of on the screen. And so let's go ahead and add 371 decimal to 465 decimal using 64 bits, or not 64 bits, 16 bits. The answer should be 836, which will be 344 in hex. And in this addition, no flags will be set. So here's one way to do this. I could actually move into a CPU register the decimal value 371. Let's go ahead and put it in R4. Okay, and this will be put 371 into R4. Kind of self-explanatory, but whatever. Now let's move the number 465 decimal into R5, and then we'll go ahead and say put 465 into R5. What addressing modes are we using right here? For the source of both of these moves, we used immediate, and for the destination, we used register. Okay, but regardless of that, we know that R4 holds a value and R5 holds a value, and I can then add them together, 16-bit, and just do R4 and R5. Now, if I wanted to record that, I could say something like R5 equals R4 plus R5. That indicates that I'm going to blow away the value in R5. So if I run this, I will actually see these values. So let's go ahead and run it because it doesn't take very long. So I'm going to go ahead and fire up a debug session. I'm going to link it, assemble it, link it, and we'll come in here. And okay, there it is. Let's go ahead and go down and set a breakpoint at the first instruction, run to the breakpoint, and we're off we go. My memory browser, I don't need it, so I'm going to close that. And let's look at R4, R5, and R5. Yeah. So I'm going to step, and now 371 should have gone into R4. But remember, that is, its default is hex. So let's put it in decimal. And let's go ahead and put R5 into decimal also. And now if we step again, we see our two numbers go in there, 465. So if I hit this next step, it's going to add these two numbers together, and I should get 836 if I add these, and lo and behold, it did it. So awesome. Not very interesting other than it worked, but more importantly, let's look at the status flags when that happened. So where is the status flag located? They're in SR. So if I expand SR, look at what I got up here. Here's my flags. So I got the 2's complement overflow flag. And if you don't know that, you can actually scroll this over or drag this over, and you can look at the name of what's happening. This is the overflow bit, and it actually gives you a description of what it does. So this one says this bit is set when the result of an arithmetic operation overflow of the signed variable range. How about carry? Okay. This bit is set when the result of a byte or word operation produced a carry. So this gives you what's happening there. And we want to watch those as we execute these instructions. And this kind of teaches us what's going on. Okay. Now let's go ahead and stop this and let's do another example. I'm going to bring back here and let's do a couple ones where in hex where we have carry or not carry, and also some that might generate the negative flag. So let's go over here and let's do this. Let's go move.w, and I'm doing example number 2 here. So let's do pound FFFEH, but remember, you can't start it with a letter, so I got to put a 0 there. And let's go ahead and let's move that into R6. And now, you know what? Let's just go ahead and add pound 1 to it. And I can do 0001 hex just to be explicit. And then I'm going to do R7. Notice in this instruction, I went ahead and I used the source as R6 has the value in it. It has FFFE in it. And I'm going to go ahead and use immediate addressing for the source of the add, and I'm going to use the destination as R6, and the sum will go back in R6. So I was able to do an add with fewer instructions, and that's fine. You can do whatever you want. So what I'm going to do is I'll do put FFFE into R6, and then my comment for this will be R6 gets 1 plus R6. All right, and we'll see what happens. Okay, let's do the other one. Let's do example 3, and then we'll run this at the same time. So I go move.w, and let's go pound 0 FFFF hex into, I don't know, let's do R7. And then we'll do let's go add.w pound 1h. And this time I'm going to list it a little different so you can see you don't actually have to fill the leading zeros in there. And we'll go ahead and put the sum back in R7. So as always, comment this. So put FFFE or hex into R7. And then down here, we'll go R7 is going to be equal to R7 plus 1. Okay. All right. So let's fire that up. Go ahead and debug that, and let's watch what happens. Okay, now on the screen, I want to be able to see all these registers. So let me scroll down a little bit. I can see the status registers, and I can see our 4, 5, 6, and 7. And down here's my main program. Let's go ahead and run to the breakpoint that we have. Nope, run to the breakpoint, not step. And so now I'm going to step, and I see 371 went back into here. 465 went into R5. I add them together and I get my result. That's fine. Now I'm going to do the next one. So this is example 2. I put FFFE into R6, and now I'm going to add 1 to it. And I want to think about what's going to happen here. I'm going to step this. The sum was FFFF. Okay? There was no carry, so the C is 0. The result was not 0, so Z is equal to 0, but it was considered negative because the most significant bit of the 16-bit sum is a 1. And if I wanted to see that, I could put this into number format and do binary, and then I would have to scroll this over a little bit. And I see all these 1s in binary. This most significant bit is a 1. So that means it is a negative number. Now, whether or not we use that or not, who knows? Well, it's up to you depending on what you're doing. But it worked. There was no 2's complement overflow. Now let's go ahead and go back No, let's step to the next one. So now what I'm going to do is I'm going to step, and we're going to put FFFF into R6, okay? No, excuse me, R7. And now I'm going to add 1 to it. And what's going to happen? The sum of this is going to be 0, 0, 0, 0, but you're going to have a carry, all right? So here we go. I'm going to step this, and I got 0, 0, 0, 0. Look at the carry was asserted. Look what else was asserted. 0 flag was asserted because the result was actually 0, and it is now not negative because the most significant bit is a 0, meaning it's a positive number. Okay, this is pretty cool. This is pretty cool. Let's go ahead and stop this session, and let's go ahead and do some more examples. Let's do the next 3 examples let's do the next 3 examples as 8-bit operations. So let's do move.b, and then I'll go pound 255 into R8. We haven't used that one yet. And then let's go, notice I didn't turn purple, so I know I had a mistake. Move.b, let's go pound 1 into R9. And then we'll go add.b, R8, R9, and the sum will go into R9, okay? And then let's do some other examples that are similar to the ones above. Move.b, and we'll do, let's see. Let's do this one. This will be interesting. -1 into R10, and then let's add to it 1 and put the result in R10. Okay, so that, look at, I can actually put a negative decimal number in there, and that's fine because it's just interpreted as a decimal integer. And then finally, let's do one where we go like move B, and then we'll do pound 127 decimal into R11, and then we'll go move.b, and we'll go pound 127 into R. No, I'm going to add 127. This last one is going to set the V flag, so we'll just be able to see that. Okay? And R11. All right, so we're going to add 255 to 1 by putting them both in R8, R9, and add those. Then we're going to put -1 into R10, add 1 to it. The result will be 0. And then we're going to do 127 plus 127, which is going to result in a number that is outside of the range of numbers that can be held in an 8-bit 2's complement number. Okay, fire it up. Go ahead and save that, and let's walk through this. Okay, so now here we go, and let's take a look. So I'm going to come over here, and now I need to see, I'm going to have to scroll around a little bit here. Let's go ahead and remove our breakpoint right there. Come down here, I remove the breakpoint, and now I'm going to add my breakpoint down here where I'm about to do my 8-bit operation starting with register 8. So I'm going to run to that, and it'll stop at my breakpoint, and now what I got to see, I want to like see my instructions in the registers at the same time. I think we'll have to scroll around since the screen's too small. So let's see, R8 is going to go in here. And you know what? R8, R8, R9, and R11, we're going to use those, right? Let's go ahead and put them all into decimal right away. So put those into decimal, okay? All right, and so we're now ready to do our first step. Let's go ahead and step it. And 255 went into R8. 1 went into R9, and now when I add these, the result is going to be 256, but that doesn't fit in 8 bits. So the answer is actually going to be 0 with a carry. So now if I can have that on the screen here, let's see, I'm going to step. Look what happened. R9 is 0, but the carry was set. The sum was a 0, so negative is, or the negative is not set, so it's not negative, but the answer is 0. Interesting. Let's go ahead and do the next one. And remember, this is 8-bit operations, so these flags are set based on the 8-bit operations. Move B into R10, 255 decimal. Let's see if I can get that in negative. So this is going to be, it's signed integer. Oh, very helpful. So now it's a signed integer, but it still left it at 255. So I guess we just have to keep that in. We have to know what's going on. So yeah, thanks a lot. And now let's add 1 to it. So we're going to -1 plus 1 is going to result in the answer 1. So if I, excuse me, 0. Well, lo and behold, it did it. So the answer was 0, even though it was a negative here. Notice that. That was nice. 0 was asserted. Carry was asserted. Life is good. And now let's do the last one. And let's scroll up here and make sure V flag. V flag is not set right now. Okay, V flag is not set. And we're ready to do this. So let's see if we can see R11 on the same screen as the V flag. Okay, so I'm going to come here. Okay, we got it. So let's go ahead and step. We just moved 127 into R11. And now we're going to add 127 to it. And the result is going to be 254. That works if it's unsigned. But if you're using signed numbers, that results in a 2's complement overflow because 254 doesn't fit within the range of 8-bit 2's complement numbers. Remember, 8-bit 2's complement numbers only go from negative 128 up to positive 127. Now, this is the first case where it's like, well, what am I using? Am I using signed or unsigned numbers? And the answer is, that's up to you. You decide what you're using. If you're using if you're developing a program that needs signed numbers, you have to keep track of the 2's complement overflow flag. That's the burden of the programmer. If you're using unsigned, then you don't care about that. Okay, so it's up to you. All right, great. So that was it. You did it. You actually have done a bunch of arithmetic. Actually, you didn't do a lot. You did adds, but we showed the status register. And we also looked at how the status flags are calculated. And we started thinking about this whole notion of 2's complement, codes versus unsigned codes. And you did it. All right, congratulations. That's it for this video. Remember, subscribe to my channel to stay up to date, and I will speak with you later.